Today we will discuss on time and space complexity of algorithms. So, let us first understand the basic definitions of time and space complexities, and then we will take few examples in order to determine how the space and time complexities of algorithms can be computed. Now, the time complexity. See, time complexity is basically the estimate of how much time would be taken by my algorithm on real machines, right. Mind you, when we say that how much time would be taken by the algorithm, this is just a theoretical estimation. We will not talk about what would be the actual run time of my algorithms, simply because I have not yet implemented my algorithms. It is before or prior to the actual implementation. So, time complexity is basically a theoretical estimation, where we try to understand that how my algorithm is going to behave with respect to increasing values of n, right. Like for example, we can explain this. So, if I say that my algorithm is suppose f n, and suppose f n is for example 2n plus of 3. So, I would like to understand that how this function f n, which contains the number of computations in the form of 2n plus of 3. We have already learned in the first lecture that how we can express an algorithm into a function. So, this function as of now contains what? The number of computations, the number of operations. So, by time complexity we mean that we would like to understand that how this function algorithm is using the number of operations, or how this number of operations are increasing with respect to increasing value of n. So, at this point of time, anywhere we are not talking about the exact computational time, right. We are rather talking about how the number of computations would scale up with the increasing value of n, and this information is of great importance to us. We will see how. Now, how actually this is done? The time complexity is basically estimated by what? Counting the number of elementary operations. And what are elementary operations? We did that in the first lecture, that rather than counting, rather than applying the step count method, where we count the frequency and the total count for each and every step, we rather pick up the elementary operations. So, the time complexity is nothing but that how these elementary operations are being scaled up with increasing values of n, and that is how we compute the time complexity, right. Now, in order to compute the, or in order to determine the time complexity of the algorithms, we use asymptotic notations. And what are asymptotic notations? We did in the previous lecture. So, by use of asymptotic notations, we can understand the rate of growth of my algorithms, and by understanding the rate of growth of my algorithms, I can make some kind of conclusion that how my algorithm would use the number of computations or number of operations with increasing values of n, and that would be a good indication about whether what or how the algorithm is going to grow or scale with the values of n. Now, this time complexity, when we talk about these time complexities, which is theoretical in nature, we ignore all the machine dependent parameters. We do not take into account any of the environment, because at this level we have not yet implemented the algorithm. So, I am not actually aware of what would be my computing environment, what would be my operating system, what would be my processor. So, this is absolutely a theoretical estimation, where we ignore all the machine dependent parameters like operating system, processors, hardware, everything, right. Similarly, the space complexity. In the space complexity also, here the context would be in terms of the usage of memory variables. So, again we would like to understand that how my, suppose this is the case. Now, here this f n is 2n plus of 3 means the amount of memory variables or amount of data that I am using with respect to a given input size n. So, I would like to see, or I would like to understand that how with increasing value of n, how these number of variables or the data portion would be used up or would be scaled up as the value of n would tends towards infinity, again the rate of growth of my algorithm. So, in this case also space complexity, we actually are doing everything in terms of your theoretical estimation. There is nothing like we are picking up each and every variable and computing the memory required by algorithm on the actual machines, right. So, again all the hardware and your environment is missing here. We only take into account the input size to the algorithm. Now, at any point of time for a given algorithm, there can be different ways where I can talk about, or I can what are the ways in which the memories can be used. So, one thing can be your variables. So, variables can take up the memory, it can be constant, it can be your temporary variables. Another way, the program execution, the program instruction would again take up some memory. So, this is another aspect where the program instructions can take up some memory, and as well as the program itself while it gets executed. So, for execution also it will take up the memory. So, these are the different three different aspects where the memory can be used up while the algorithm is run. Now, at times students get confused between the two terms. One is your auxiliary space and other is your actual space complexity. So, auxiliary space is nothing but the additional memory that is being taken up by the algorithm. So, if the algorithm has, for example, if the algorithm we are using an array A and suppose the input size of the array is suppose n. So, if other than these we are using any other, say suppose temporary variable or temporary array B, then this B would be called as what? An auxiliary space, right. So, if we sum up the things, this space complexity is nothing but the auxiliary space plus your actual input space. For example, here if in the algorithm I am using the array A and n, so this would be called as the input space, and if this B array is used additionally, then B would be called as what? The auxiliary space. So, the sum of these two would be called as what? The space complexity of the algorithm. Now, let us talk about some of the very common time complexities that occur, and information and knowledge of these time complexities is very important in order to understand the entire concept. So, the first and the most common is your order of 1 time complexity, which is also called what? A constant time complexity. When we say constant time complexity, it simply means that the instructions or the operations into my algorithm does not anyhow depend upon the increasing value of n. It does not depend upon the input size. It is independent of the input size, right. For example, in this particular small code, we can see that we have passed an array A, right. Now, for this particular array, whatever may be the size of the array, whether it contains 10 elements or whether it contains 1000 elements or any amount of size, it would always print the first element of the array. So, it is not at all depend upon any of the size of the array. So, therefore, this printing statement would take what? A constant amount of time, right. So, therefore, this comes under the category of a order of 1 algorithm. So, when we say order of 1 algorithm, we would mean it is a constant amount of time. That constant can be a small constant and that constant can be any big constant, right. So, whatever may be the size of the constant, it is a tradition to write order of 1, which is called as a time complexity of constant time, right. Again, the loop itself can also be considered as what? Order of 1 time complexity. Like for in this example, we have taken a loop, but this loop is iterating for a constant number of times only, where C considered to be a constant. So, this is also an example of a constant runtime algorithm. So, loop can also be considered or can be put under the constant time category in this example. Now, next is your linear time complexity algorithm. In the linear time complexity algorithm, the time increases linearly. It means, in simple ways, if we have the function fn, then it can be represented as in simple manner like this way, where C is the constant. So, this function would increase at most linearly with respect to a constant C. This constant C may vary, right? This constant C may vary, and this function say suppose G can be expressed or can be of any nature, but it has to be what? Only of linear nature. For example, instead of n, I could have what? 2n plus of 3 or any kind of linear nature. So, the highest order term has to be n, right? The highest order term has to be n. So, for example, I have taken, this is a very kind of common situation where we iterate through an array and we search for an element within the array. So, where we use the entire array size, so in that case the linear time complexity comes out to be the best possible algorithm, where we search the element in a sequential manner. For example, in this case, here what we are doing is we have passed an array, ARR, and what we are doing is we are printing the each and every value of this array in a linear fashion. So, if suppose the I goes from I to 10, so I have to print each and every value of AI from I to 10. So, this is an example of linear algorithm, linear time complexity algorithms, right. Now, this function order of n, where I is the number of items in the array. Other than this linear time complexity algorithm, there are a number of examples where such kind of scenario occurs. For example, traversing an array. For example, if you want to traverse a linked list or an array or even a list. So, these are all examples of linear time complexity algorithms. For example, if you are comparing two strings, so you have to compare the strings by reaching towards the length of the string, checking for palindrome, for example, counting in bucket set, or these examples comes under the category of your linear time complexity algorithms. Another example, you can see here this the array goes from, say, suppose I to less than n. So, the total strength of this loop is suppose n, and we are doing what? We are summing up each and every value of I with the help of a sum variable. So, the total time complexity comes out to be order of n. Now, the next is your order of n square time complexity. Now, this kind of time complexity is very common, where we are using what? Nested loops, loop within a loop. So, if you have a loop, if you have an outer loop, we also have an inner loop which regulates or gets under the first loop. So, for example, here we have seen you have taken an algorithm where we have passed the array of size n, and so we have taken an upper loop of I which goes to n, and again we have taken embedded loop of j which again goes till the size of the array, that is n. So, for every value of I, j would be executed from 0 to n, right, from 1 to n, that is n times, right. So, in this case the time complexity would be what? N would be coming from the for loop, from the first loop, and another n would be coming from the second loop. So, it would be a time complexity of n cross of n. In a simple words, if suppose I have, say, 10 elements, then I have to print those 10 elements what? 100 times, right. So, this is a case where the time complexity of the algorithm comes out to be order of n square. Here are a few other examples, like over here what we are doing is there is small variation to the previous example. In the second loop, what we are doing is j is going what? Less than till I. So, if I iterate this and if I jot down the iterations, so when I is suppose 0, so this j would be executing what? 0 time, because of this particular condition, j has to be what? Less than I, right. When this I is 1, this according to this condition, j would be iterating what? 1 time. And similarly, if we list down the series, the series would come out to be this, and by solving this series, the final term would be n into n minus 1 by 2. And if we are going to see, the highest order term in this particular term is what? N square. So, the total time complexity by the order of growth of the algorithms would come out to be n square. So, this is an example where n square algorithm has been written. Similarly, over here also again a small variation in the second loop. The j loop has been iterated what? Less than k times. K can be a constant or k can be any other value, right. So, here the n iterations would come from the first loop and k would come from the second loop. So, the time complexity would be what? Order of n cross k. If k is equivalent to the size of n, it would become a order of n square complexity. Let's now talk about order of log n time complexity, which is also called logarithmic time complexity. Now, in this case, in every iteration, the number of iterations are decremented either by a constant factor, like in this particular case, what we are doing is we are doing what? We are multiplying, in every iteration we are multiplying I by a constant factor c, and in the second case what we are doing is we are decremented the each and every iteration of I by a constant factor by division of C. So, in such cases we use the logarithmic time complexity, and how it happens. For example, in this particular example, if we start with I is equal to n, so in the second phase this would be decremented by a constant factor of 2, that is n by 2, and this is manner, in this manner it will go till 2 raised to the power of, say, suppose I. So, at some stage this would be equal to 1. So, if I represent this as n is equal to, or n by 2 raised to the power of I is equivalent to 1. So, at some point of time I can represent this I is equal to log n by how n is equal to 2 raised to the power of I. So, by putting I as log n. So, this is how this time complexity can be determined. So, this is again a very common time complexity that we often take, or that often occurs in your algorithms. The basic idea is not using the complete data and reducing the problem size with every iterations. That is what we did in both the examples. Now, similar kind of complexity, as similar to your log n complexity, we have another form of complexity which is called order of log complexity, right? That is log n time complexity. In this case, the loop variables is reduced exponentially by a constant amount, right? So, here we are talking about the exponential reduction, and in that particular case we were talking about the reduction by a constant factor. Like for example, in this particular case, what we are doing is, in every iteration what we are doing is I is incrementing, or I has been incremented by a factor of I is equal to what? I raised to the power of C, where C is a constant value. So, in here also the loop gets decremented by a factor of I raised to the power of C. So, in such cases we can represent the time complexity to be what? Order of log n complexity, right? Another way of doing so is, or another form of it is, like in second case, this I is decremented by a factor root of I. So, in both the cases, if such cases occur, we can always put them into the category of order of log n time complexity. Now, let us see how this log n and log n time complexity can have an effect on our algorithms, or for a particular example. For example, suppose I have taken the number, suppose 653,536, and how many times I have to divide it by 2, right? So, until we get down to suppose 1, if this is the case. So, if I have listed for the log n case, in log n case what we are doing is we are decrementing in every iteration by a constant factor of suppose 2. So, it would take how many steps? It would take around what, 16 steps to reduce it to what? To reduce it to 1. So, this is an example. So, this is an example where we are talking about log n case, right? So, this is the entire example for log n. Now, if we take log n complexity, then it would take only the 4 steps to do so, because in that particular case what we are doing is, in every iteration we are reducing it by a factor of root over of, say, the n, right. So, in this case we would hardly take what, 4 steps. So, this is the amount of difference that can be created by using log n complexity and by using your log n complexity. So, this is just for your information in order to understand that how these two can be distinguished. Now, other complexities can be your polynomial time complexities. In fact, n raised to the power of k complexity comes under the category of your polynomial time complexity. So, n can be k can be your 3, it can be 5, it can be any quantity, right. So, these complexities are actually termed under polynomial time complexity. As far as the exponential time complexity, which is not acceptable, or which is not acceptable in most of the cases, it is not a good complexity, it is of the nature of 2 raised to the power of n. The most important part is that you need to understand this ordering among the various time complexities. So, by looking at this particular ordering, you can always say that order of 1 time complexity is more preferred, and it is one of the best time complexities as compared to other time complexities. So, at any point of time, if I have a complexity of suppose order of say n log n, and other algorithm is of suppose order of n square. So, we can clearly understand that which of the algorithm would be better, And this can also be done by plotting the graph between both the complexities for different values of n, and see that which of the algorithm is growing faster and which of the algorithm is growing slower. Now, another way of putting the things, suppose I have two loops, right, and both the loops are separate loops, they are not embedded loops. So, if in case I have to determine the complexities in this case, so for the first loop, the strength of the first loop comes out to be suppose m, and for the second loop the strength comes out to be suppose n. So, what we can do is, if we have to list down the time complexity of the entire algorithm, so normally what we do is we sum up the time complexity of both the cases. So, we would add up order of m plus order of n, which can be stated as what, order of m plus of, if in case both the terms are of equivalent nature, suppose m is of equivalent to n, so it comes out to be 2n, which can be termed as order of n time complexity, right. Now, next, by looking at this particular graph, you can have a understanding on how the various time complexities grow with respect to the input size. So, at least you should have an idea that how the various complexities are plotted with respect to increasing values of n. This is just for your additional information. Now, thing is, why we should actually worry about these complexities and how does it matter actually. So, if you look into this particular table, you would find that when the values of n becomes very large, it can matter a lot. For example, in this case, if you find that for 10 raised to the power of 6, which is not a very big quantity, for this particular case, for the time complexity of suppose exponential time complexity 2 raised to the power of n, the things can be absolutely uncontrolled, right. So, this is the kind of effect it can create. So, complexities does matter, especially when the values of n becomes very large. So, that is the reason why we talk about the time complexities, and that is the reason why a lot of efforts goes in at the algorithm level and at the coding level to improve upon the time complexity, to reduce the time complexity, right. So, at least we have an idea about that which of the time complexity would be better and what we should actually target for. So, normally we should target for the complexities which are polynomial in nature, and that too the time complexities which have a slower rate of growth as compared to the time complexities which have a higher rate of growth. So, if you have an algorithm with a higher complexity than necessary, then no clever programming will make up for it. For example, if you have designed an algorithm and if that algorithm has a time complexity of suppose order of n cube. So, whatever intelligent programming or intelligent steps you may put into the algorithm, it would be very difficult to control the behavior of the algorithm. If it is order of n cube algorithm, if you have used 3 embedded loops and the complexity is of suppose n cube, so whatever efforts you may put in, the complexity will not change, right. You may improve upon some of the constant factors, you may improve upon certain aspects of the algorithm, but the time complexity would remain same, and that would always be a point of hindrance if that time complexity is very large. So, let us see what we have learned today with a small quiz. So, we will take a few questions. In the first example, we have been asked to determine both the time and the space complexity for the following piece of code. So, if you look at this particular code, we have a simple for loop which goes from 0 to n, and we have done a simple expression where we are doing what, x has been incremented by a random factor. And similarly, we have another second loop which again goes for till j is equal to 0 to m, and again similar kind of operation has been done. So, what is the time complexity of this algorithm? So, in both the cases, this strength of this loop is what, n times, and the strength of this loop is what, m times, right. So, if we talk about the complexities, since these are not embedded loop, these are separate loops, this loop is not coming under this particular loop. So, therefore, the time complexity would be m plus of n. So, in this case, the time complexity would be what, n plus of m first. And as far as the space complexity is concerned, and what would be the space complexity in this particular case? Space complexity, now in this particular case, the size of the input was suppose n, right, and other this n, we have not used any additional memory space. other than this n, we have not used any of the additional space, right. In similar case, the second loop also, other than this m, other than this loop, that is the array size, we have not used any of the additional memory space. So in both the cases, the space complexity would remain constant, and therefore the answer C or answer 3 would be the appropriate answer. So order of n plus of m, and the space complexity would be of order of 1. Let us take another example where we have been asked to determine the time complexity of the following code. So in this particular example, we have an embedded loop. In the first loop, the size, the strength of the loop goes what? Till n times, and the second embedded loop has also a strength of suppose n times. So, and a simpler expression has been given where C has been added, we are adding x and y quantity with every iteration of y. So in this case, what would be the time complexity? In this case, the time complexity would be the, since this is embedded loop, so the answer would be what? Answer would be n into n. So the time complexity would be n cross of n, order of n cross of n, which can be stated as order of n square algorithm, right. We can always list down that how this n square has come. Like for example, in this case, when x would be 0, this would be iterated what? How many times? It would be iterated n times. Y would be iterated for n times. When x would be 1, it would go n minus of 1 time. In similar way, if we list down this series, it would come out to be n into n plus of 1 by 2, which talks about the highest order term in this case would be n square, and therefore the complexity would be order of n square complexity. Another example. So what does it mean when we say that algorithm A is asymptotically more efficient than algorithm B? So when we say that A is asymptotically more efficient than B, so it automatically means that A has always a lower rate of growth as compared to algorithm B. When we say that algorithm A has asymptotically more efficient than B. So mind you, whenever we say that algorithm is better than other algorithm, that better algorithm will always have a slower rate of growth with respect to the bigger algorithm. So in this case, the answer 2, that A will always be better choice for the large inputs, and we normally talk about the efficiency of the algorithms for larger values of n as per the definition of rate of growth of the algorithms, where we talk about how the algorithm behaves for larger values of n when n tends towards infinity. Another question, what is the time complexity of linear search algorithm? As you know that in linear search algorithm, we need to iterate, we need to find the element from the starting position of the array, and we start looking for the element for the from every iteration of the loop. So definitely in the worst possible case, it could be the case when the element is not found and we have to iterate for each and every element of the array. So therefore the entire size of the array would come into play. So and therefore the time complexity can be stated as what? Order of n time complexity, right. Another example. So here what we are doing is, here again we have a loop where in every iteration what we are doing is we are decrementing it a factor of 2, right. We are decrementing this by a factor of 2. So this is how it would be given. So obviously we have already discussed about this. In this particular case, this is purely a logarithmic series where we are decrementing the steps in every iteration by a factor of 2, and this can be termed as a log n complexity algorithm, right. Now let us talk about something about space complexity. Now when we talk about space complexity, as we have already understood, that we actually predict what could be the amount of variables or what could be the amount of data and how this data has been used up with increasing values of n. So let us take few examples. In the first example, what we are doing is we have taken 3 different parameters, int x, int y and int z. So other than this variables, we are not using any of the additional space over here. There is no auxiliary space other than the value r. So other than this x, y, z, we have additionally taken what? R. So R is the additional space that we are taking in addition to x, y, z. So for x, y, z we have what? 1 memory unit, so it comes out to be 3, and 1 additional for the local variable R. So since if we add up all these terms, it would be a constant time. So therefore this comes under the category of order of 1 space complexity. In this example also, we have passed the array, we have passed A as the array as a parameter, and we have passed the input size as n. So in this case also, what we are doing is we are using the entire size of the array. So the space complexity can be maximum of order of n. And additionally what we are doing is, other than a and n, we are using the variable I as an additional space, which is nothing but a constant. It would add up to a constant value. So the major term over here is order of n. In third case, again we have passed an array and integer variable n. In this case also what we are doing is, they requires n units for r and plus 1 plus space for n, k and I. So these are 3 different variables which are additionally being used. So again this adds up to a constant value, so the major term would be order of n. So in both the cases we must know that how the variables of the data portion is being used, and whether it is the additional space or whether it is being consumed within what has been passed to the algorithm. There is another example here. Here also we have passed in the array A and we have taken the input n of size n. So here, since this array A is of integer type and n is of integer types, so considering that every integer will take up 2 bytes, so 2n bytes for each and every element of array A, right? Then it is using n memory units of its own space. So we have passed the array A of size n, so it is using what? N memory units of its own space, right? And 2 bytes for the 3 different variables that are being used in the algorithm, that is x, n and I. So the total space that can be stated is what? 2n plus of 8. So this is more exact nature, where we have listed down what could be the amount of memory that can be used for each and every type of variable. For example, in this case we have used the integer variable. And similarly for this particular case also, again we have passed what? 3 integer type of arrays and integer variable n. So again in this case also what we are doing is, it is requiring n units for x, n units for y and n units for z, and 1 unit for each I and n. So if we list down the complexity, it comes out to be 3n plus of 2. So these are very simple cases. You can always learn, you can always practice that how we can list down the algorithm and how we can find out the space complexity of various instructions. You can always go through this example based on what we have learned so far. Again one more example. In this case what we are doing is, we are passing 3 parameters a, b, c, and since no additional space has been used, so this is an example of, if we consider that each and every variable of a takes up a constant amount of time, so it would be what? Order of 1 plus order of 1 and plus order of 1 for c. So total of order of 1 time complexity can be listed, right? Similarly for the second example, again in the second example what we are doing is, we this particular case the total of complexity would be what? We are using the entire size of the array here, so therefore the time complexity would come out to be order of n, and the auxiliary space would be what? Order of 1, because other than this a and n I am using what? The additional variable of s, which can come out to be a constant order. So we can practice these kind of questions, and you can always see that the more you practice, you would be more in acquaintance with that how we solve these kind of problems, right? I would suggest you to go through this small quiz. These are similar questions that we did in the part of a lecture. So try to solve these questions. In case you have any issues, then you can always get in touch with me. These are some important references that I have listed down. Try to go for very good examples on your geeks. There are very good questions on available on the code chef also. So try to see these various links. It may be helpful for you all. So in case of any queries, you can always get in touch with me. Thanks a lot. Thank you very much.